Have you ever wondered why when you're watching, say, an emergency vehicle, an ambulance, or a fire truck coming down the road towards you, that while it's coming towards you, it sounds like it's a higher pitch, and then as it moves past you, it sounds like it's a lower pitch? You know, because I am a emergency vehicle here, it comes at you, it goes, "Eeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeee So what is that effect that when it's coming towards you, a emergency vehicle, a siren, a sound wave, as it's coming towards you, you hear a higher pitch. And then as it moves past you, you hear a lower pitch. That is what we call the Doppler effect. And it's a property of any wave. It is a relation between waves and motion. As it's moving towards you and you hear that higher pitch, you're actually experiencing shorter wavelength sound waves. And as it moves past you and away from you, you're experiencing lower pitch, longer wavelength sound waves. So if this just works for waves and light is a wave, does the Doppler effect happen for light? The answer is absolutely yes. So in this video, we're going to connect light to observations. And we're going to bring this around to spectroscopy of how we can measure spectral lines to determine motion of objects in the universe. All right, so this is our video on the Doppler effect, which you can think of as our universal speedometer, the thing that can measure speed and motion. I just want to go ahead and show you the quick little animation just to prime us all and to give us a definition of what the Doppler effect is. This is mostly what I have in the notes, which I assume you have all already read through. So this is just review at this moment. So the Doppler effect is that the observed wavelength, and remember that's equivalent to frequency. It's almost a little bit easier to talk about the Doppler effect in terms of frequency than wavelength. But the observed wavelength, the observed frequency of any wave, so light waves, sound waves, changes with the motion of an object toward or away from you. So it could be the source of the wave is coming towards you or moving away from you, or you yourself are moving towards the source or away from the source. Doesn't matter who's doing the motion, as long as there is some relative motion between where the waves are coming from, what is emitting the light, what is creating the sound, and you, the observer. And that's what this is trying to show you down here, that here you have our observer or our source, and what you're seeing is each ring that you're seeing as it expands outward is the crest of a wave. So you can think about it as sound waves or light waves, and they're just spreading out evenly like ripples on a pond all around the source. And then here you have an observer that is the source is moving towards, and here's an observer that the source is moving away. And you can see it looks like the distance between these wave crests, the wavelengths, is longer for motion away and shorter for motion towards. So our wavelengths look compressed over here, and they appear to be at shorter wavelengths. And over here, they appear to be at longer wavelengths. Well, I think this is a great picture that does the job. I always picture this a little bit differently in my brain, so I wanted to walk you through how I've always pictured this. So I'm gonna have a series of slides to show you how the Doppler effect works. We have our favorite observer, or our favorite person for this experiment. We have Dr. Lindsay's cartoon Galileo. We have a light source over here. So we're going to see waves of light streaming past, where each one of these vertical lines represents a crest of the light wave. You can think about it as sound waves if you want to. So Galileo's job right here is to count the number of crests going by every second to measure the frequency. Or you can think about how far apart does it appear the crests are to him. A little bit easier to think about this one in frequency. So what I'm going to do for each one of these is I'm going to send in a beam of light at our cartoon Galileo. And that beam of light is going to have a wavelength of 500 nanometers. It's just going to be sitting still. So if we had a laser beam that shoots 500 nanometer light, we call that the rest wavelength. If there's no relative motion, that's the wavelength that we measure, 500 nanometers. So in this case, there'll be no motion at all. So so our observer should just be able to measure the wavelength of this light beam to be 500 nanometers. So measuring the wavelength, really measuring the frequency and translating it to wavelength, since he knows the wave speed, and observes the rest wavelength of 500 nanometers. There's no motion involved other than the wave itself going past Galileo. All right, so in this next one, we're going to have Galileo move towards our source. So here comes our wave crest coming from this side, and Galileo is going to move towards the source. Now, as he does that, he's encountering each wave crest quicker. It's wave crest, wave crest, wave crest. So let me try that again. Crest, 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 crest. So you can see as he's moving towards the source, it looks he would measure all those wave crests closer together. They get all scrunched up. So he would observe not the rest wavelength of 500 nanometers. He would observe a wavelength of 450 nanometers, a shorter wavelength. And remember, in the visible spectrum, if we're moving to shorter wavelengths, we're moving towards the blue end of the spectrum. So we say, in this case, that the Doppler effect has blue shifted the light. So each one of these wave crests is 500 nanometers apart. He could translate the frequency. It tells you how often he counts wave crests. And if he's moving towards them, he counts them a lot faster. So there'd be a shorter wavelength. They appear to be a lot closer together. And in that case, instead of measuring the rest wavelength of 500 nanometers, Galileo would measure a wavelength of, say, 450 nanometers. And then this second to last one, I'm going to have him move away from the light source. So now we have motion away from the source. And as he moves, he's moving the same direction that the wave crests are, so the wave crests have to catch up to him and pass him. So if he was counting wave crests, that would happen much, 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 much slower. So in this case, it would be wave crest, wave crest, wave crest, wave crest, wave crest. So he measures a longer wavelength. Those waves appear to be stretched out. So if he was measuring light, instead of measuring, say, 500 nanometers, the wavelength, the rest wavelength of this light beam from the light source, he would measure that having a wavelength of 550 nanometers. He literally would see that the light looks to be more red, towards the red end of the spectrum. So in this case, we say that the Doppler effect has red shifted the light. One more time. So it looks like all those wave crests are getting stretched out, which for light, that means that he would measure, for him, he would see a longer wavelength, which literally means that he would see redder light. In the blue shifted case, he would see the light as bluer. And finally, so we've done motion towards, we've done motion away. What about side-to-side motion? In this case, it would be up or down on the screen. So-called transverse motion. So in this case, it's just as the same as the rest case. He still measures the wave crest, this the same as he would in the rest case. So he would measure the wavelength of 500 nanometers. No Doppler effect is observed for side-to-side motion. It's only motion towards and away. Which brings me to a couple of definitions. The Doppler effect is only observed for motion towards and away. And we could just see that with the animations that I went through. Motion that's towards or away, so you moving towards the source or you moving away from the source, or the source moving towards you or the source moving away from you, that is called radial motion, directed directly towards you or directly away from you. And that's where we observe the Doppler effect. So we only observe the Doppler effect for so-called radial motion, motion towards or away. Side-to-side motion, so-called transverse motion, a motion perpendicular in the direction, so side to side. In that case, we do not observe the Doppler effect at all. So the Doppler effect can detect motion, but it can only detect a certain kind of motion. It can only detect motion that's towards you or motion that's away from you. It can't detect side-to-side motion. You don't get a Doppler effect. You don't get any apparent change in the wavelength of whatever it is you're observing. In astronomy, it's light, so you don't see any apparent change in the wavelength of light. For radial motion, you absolutely do observe a change in the wavelength of light. So for radial motion towards, the Doppler effect will shift the wavelengths to shorter wavelengths. Astronomers call this blue shifted, or blue shift. For radial motion away, the Doppler shifts the wavelengths to longer wavelengths, and we say that this is a red shift. We have our own sort of terminology here that we use whenever we're referring to the Doppler effect. Blue shifted means motion towards. I'm observing wavelengths shorter than the rest wavelength. Red shift means that it's motion away. I'm observing wavelengths longer than the rest wavelength. And if you're going to change your speed, so you're going to go charging towards that source faster, you'll encounter those wave crests quicker and quicker and quicker. You'll measure a shorter and shorter and shorter wavelength. So the faster the motion, the larger the Doppler effect. Notice that works for movement away as well. The faster you're moving away from the source, the more time it will take for that next wave crest to catch up to you. So we will observe a more extreme version, a larger red shift or blue shift, as our motion towards or away increases. So not only can we detect motion, we can detect the speed of the motion. And yes, we can actually do this. This is how you get speeding tickets. Whenever you have someone that's aiming a radar gun at your car, they're sending out a radio wave, a light wave, at your vehicle that's going to bounce off your vehicle and come back. And whenever it bounces off, you're moving towards the source of the waves. So you're going to be moving towards it. What it's going to do is that radar gun shoots off a single wavelength of radio wave light, or a very narrow range. It'll bounce off. Since you're moving towards the officer, it's going to blue shift, move that radio wave to shorter wavelength, go back into the detector, and that will actually translate to a speed by how much the wavelength shifted by. And if it shifts too much, you get a speeding ticket. If he's aiming the radar gun at you as you're driving away, they bounce off, the radio waves get red shifted, and that can be translated to a speed as well. Now just a little bit, so in this animation or in this picture up here, not animation, this really would work. I like to picture just say a star up here, and if that star is barreling towards us or you're barreling towards that star, okay, in fact, let's put on our imagination caps. Let's imagine that we're in a totally awesome spaceship that I have, because, you know, Dr. Lindsay needs a spaceship. I keep it in the hangar that doesn't exist. So we go get Dr. Lindsay's spaceship and we launch ourselves into outer space and we start moving really, really close to the speed of light. We're zooming through the stars. You head to the front of the ship where we're barreling towards the stars in front of us. Those stars would appear blue. Even if it was a white star, that star to us would look blue. You'd run to the back of the spaceship where we're zooming away from the stars behind us. All of those stars would look red. And yes, this really does happen. We can measure this. The Doppler effect is real and is giving us a way to detect motion. But how do we actually do this in astronomy? Why are we talking about this right after I talked about spectral lines? So because with spectroscopy, measuring precise wavelengths, looking at light as its component wavelengths is how we can measure the Doppler shift. And knowing something like we know what the lines of hydrogen look like in an emission or an absorption spectrum, so we can recognize those lines, that pattern of lines, gives us a way to determine if they're at the wavelength we expect, their rest wavelength, or if they've been blue shifted or red shifted. So at rest wavelengths, here are our hydrogen bomber lines, the visible light ones. Here's that hydrogen alpha at 656.3 nanometers. Here's hydrogen beta at 486.1 nanometers, and so on and so forth. We can recognize this pattern. We know hydrogen alpha is supposed to be at 656.3 nanometers. Hydrogen beta is 486.1 nanometers. But let's say we go out there and we observe a nebula, a cloud of gas in outer space that's full of hydrogen. It's giving off an emission spectrum. We measure that emission spectrum, but we get this up here. We get hydrogen alpha. We can recognize the pattern, like, yep, there's hydrogen alpha, there's beta, gamma. But we measure the wavelength of hydrogen alpha at 657.0, hydrogen beta at 486.1. That's at longer wavelengths than we expect them to be. Oh, by the Doppler effect, we can conclude that that cloud of gas is moving away from us. We observe the emission lines as redshifted, more red than they should be, and that lets us conclude that that cloud of gas is moving away from the Earth. We measure another cloud of gas. We see that it's full of hydrogen. We see its emission lines. We find the Balmer series for hydrogen, like, yep, there's H alpha, beta, gamma. And, oh, wait, H alpha is at 655.0. That's 1.3 nanometers shorter than we expect. Oh, by the Doppler effect, that leads me to conclude that this gas cloud is moving towards the Earth because the wavelengths are blue shifted. They're all bluer than they should be, shorter wavelengths than we'd expect them to be. And I do not expect you to have to do this, but you can use the Doppler effect to actually calculate the speeds. So it's not just a motion detector, it really is a speedometer. And you can do this by a simple ratio, proportionalities really, that the observed change in wavelength, so whatever it's supposed to be minus what you observe it as, divided by what it's supposed to be, so the observed minus the rest wavelength, that's how much it shifted by, how much it got Doppler shifted, divided by what it's supposed to be, its rest wavelength, has this, it should be the same as the recessional velocity, that's how fast it's moving away from us, divided by the speed of light for light waves. You do not have to memorize that equation. You do not have to derive that equation. You do not need to manipulate that equation. But I want to show you that it works. So let's take this blue shifted case up here and let's take hydrogen beta. So what is our observed? 485.1 minus our rest, 486.1. That's minus 1. A change in wavelength of minus 1, blue shifted. Divided by what it's supposed to be, 486.1, multiply by the speed of light, and I get a recessional velocity of negative 620 kilometers per second. The negative means that it's moving towards us. Recessional velocity is how fast it's receding. So negative recession to be towards. But we actually calculated the speed. And we can do this as long as we can measure an emission spectrum or an absorption spectrum and identify things like these hydrogen lines, these hydrogen Balmer lines. You could use any element as long as you can find a line and you know what it's supposed to be. You can measure what you observe it as and determine the motion of an object. We have a speedometer for outer space now. And that's just such a powerful tool in our tool belt that I have to share some of the cool things that we can do with this. So it has a nearly endless list of useful applications. You might wonder, how do we know the shape of the Milky Way? How do we know that the stars are moving around? How do we actually measure, if we come up with it, how do we actually measure the rotation of the galaxy? If we're looking at other galaxies and we look at their rotations, that's what Vera Rubin used to find out that they're rotating too fast. They're rotating faster than we expect for the amount of mass we can see, which led her to conclude that there must be some more mass there that we can't see. There must be dark matter. How do we actually measure those motions? How do we measure the motions of the stars in our own galaxy and the rotations of galaxies in general? By looking at the Doppler shift of the spectral lines. Look at the stars of all around us in our galaxy, and you can measure their radial motions. You can get a map of where the stars are and how they're moving. You can build a map of our galaxy. You can build an idea of the rotation of other galaxies, how their stars are moving around. And you can use that to find out that there's this weird stuff called dark matter. There's 5 times more dark matter than there is the kind of matter that we're used to interacting with. We can look at the sun, and it would be rotating around and around. One side's moving towards us, one side's moving away from us, so we can detect its rotation. We can look at a exoplanetary system, an extrasolar planet, a planet in orbit around another star. We know, because we've studied Kepler's laws as modified by Newton, that if there's a planet, it has its orbit, and then a star will also have its own little tiny orbit in response. Well, if we stare at that star and it's aligned right, sometimes it'll be moving away from the Earth, sometimes it'll be moving towards the Earth, away from the Earth, towards the Earth, away from the Earth, towards the Earth. Look at the spectral lines, say find that hydrogen alpha line, and see that it gets red shifted, blue shifted, red shifted, blue shifted, red shifted, blue shifted in a very periodic way. How long it takes for it to go red shifted to blue shifted to red shifted gives us the orbital period, which, if you remember, the orbital period of the star is the same as the orbital period of the planet. So this allows us a way to detect planets in orbits around other stars. We can't see the planets directly. They're too small and dim, and they're outshone by their host stars. So these are just a few examples of how powerful and useful the Doppler effect is. Thank you for tuning into this video. We have one last one for our lessons about spectroscopy, and I will see you then.